Okay, thank you very much. First of all, I would like to thank the Academy of Science for this prestigious award, and it's a great honor for me to be here. And I wait my slides. In the meantime, I will tell you just a few words about myself. So I did my PhD at University of Bari in Italy in the framework of a common research program with the Massachusetts Institute of Technology that I was also visiting during my PhD. Then I spent several research periods abroad like a visiting researcher, some of them at University of Paris, at the Delft Institute of Technology, at the Harvard University. Actually, I am Director of Research at the National Research Council and Professor of Condensed Matter Physics at the Scuola Normale Superiore in Pisa, where I lead the group of THz nanophotonics. Just a few words about what is the topic of my research. So basically, photonics has revolutionized science in many aspects of human life recently, leading to amazing progress in the field of quantum technology, of biomedical science, of random physics, a lot of intriguing research. And certainly in the framework of these processes, the materials has played a major role for the major developments that we are dealing with in the last year. First, I would like to mention the semiconductor materials, which recently brings the quantum world step by step, and in particular, this semiconductor heterostructure, which are the core of my research activity, that are basically just a set of quantum well and quantum barriers, which are put one on the top of the other to build amazing semiconductor devices. One of the major examples of these quantum semiconductor devices is the quantum cascade lasers, which is a micrometer-sized device. It's basically built by combining together a set of barrier and wells material to build up a cascade. So the quantum cascade lasers has been discovered in 1994 at Bell Labs by Federico Capasso and co-workers. And basically these lasers has a major set of properties which make it quite unique with respect to the standard lasers that we all know. Basically because it is a unipolar lasers, which is characterized by the fact that the transition of electrons which then generate photons happens only in one band, which is the conduction band of the material, and then you can tailor all the properties of this laser, the wavelength of emission and all the physical process that can happen in it, just playing with the thickness of the well and barrier material and with the doping that you can put inside this well and barrier materials. So just inspired by all the research that has been done at Bell Labs still in 1994 and also in the other research group over the Europe, I then started to pioneer the research in the field of quantum cascade lasers operating in a specific range of frequency, which is the far infrared. And some of the major advances that we did in our group is a demonstration of a THz quantum cascade laser frequency comb, which is just, we have here in the audience Professor Ensch, which is really the pioneer of the THz frequency comb and the mid-IR frequency comb, which is basically miniaturized lasers that can emit evenly spaced set of optical modes, and also the demonstration of the first random laser exploiting this semiconductor heterostructure. So why the quantum cascade lasers is so important for applications in the practical world? Starting from the mid-IR, there are many gases, molecules, and compounds which have spectral fingerprints which call in this frequency range, so it is quite appealing for making quantum sensing, exploiting these sensors, and also for countermeasure. But this is even more appealing in the THz frequency range, which is basically just the gap in between the region of interest of photonic and electronic devices, and has amazing properties. Why the THz is so nice? It's so nice because the THz wavelength and the THz beams can basically are completely not invasive, so very differently from the X-ray, they cannot alter the issue and they are completely safe from the health. And also they can unveil the water content in a very unique way because they're strongly absorbed by water. And with this radiation, we can then make a lot of applications for security because they can penetrate through clothes, so they can detect dangerous.
Slowly, because the translation is impossible.
Okay. So they can go through my slides again. Okay, here we are. So basically this radiation can penetrate through clothes, so it is possible then to unveil some metallic objects which are hidden, for example, behind the clothes of the human. Also, nicely used in order to make some analysis of the quality of the food, because they can, for example, unveil some contaminants which are in the food. They are appealing for sensing, again, because many rototranslational frequencies of molecules and atoms fall in this frequency range. They are also quite nice for medicine and for biology, because looking to the anomalous water content which is inside the tissue, they can be predictive for the development of a cancer inside the tissue itself. And also for cultural heritage is also quite nice, because the THz can basically detect in a quite unique way the pigments which are behind a painting. And for example, this is an application in which the signature of Goya was unveiled behind the first painting layer, which is basically on a painting with this unique radiation. Then, inspired by those kind of intriguing figures, I also started to play with the new materials, not only the semiconductor materials, because the semiconductor materials has some drawbacks, and the drawbacks is that when you embed together a quantum well and the quantum barrier material, you need to respect the lattice matching condition between the two materials itself. And so very recently we started to work in my group on the development, like in a Lego game, of the van der Waals heterostructure material by using bidimensional materials that can be embedded one on the top of the other to really engineer from scratch some electronic and photonic properties of the devices. And just to give you some flash ideas of what we did, we started to work with graphene, which is the material discovered and came to the fashion from the Nobel Prize of Physics in 2010, which is basically a single layer atom that comes from exfoliation from graphite. And also we started to play with a similar to the material, which is the black phosphorus, which has quite similar properties with respect to graphene, but differently from graphene is a material which has a strong anisotropy, and this strong anisotropy can be useful to, again, engineer and decide from scratch which kind of phenomenon do you want to activate in a device. And with that, we realized some photodetectors, all operating at room temperature, scratchable over a flexible substrate, and we exploited this detector to make already some practical applications, like, for example, unveiling in a medical tablet an anomalous water contact. As you can see, this is an image reconstruction which has been done with our lasers and with our detectors. We can simply put 1 microliter of water in a medical tablet and the detector can unveil it. Or we can make, for example, an experiment in which in transmission we can look through a chocolate bar and we can unveil, for example, an anomalous presence of an aluminum foil of the packaging of the chocolate bar on the other side of it. Other fancy things that we did with this van der Waals heterostructure is to develop ultra-fast switches for electronic waves. Basically, the concepts, just to give you the idea of it, it's quite similar to what's happened when you put a stone in a water, in which you can create just some waves that start to circulate in a water, and we activate these waves in the lab by using the tip of a near-field optical microscope, sending an ultra-fast beam to the tip and starting to generate some waves, which are the surface plasmon waves over the surface of the material activated in this 2D material. And very nicely, what we discover is that the activation, the switching on and switching off of these waves happens in the femtosecond scale. So those kind of materials can really become material suitable for the development of a new generation of transistor faster than the fastest transition which exists so far. Another thing that we did with the 2D material and van der Waals heterostructure is to build up an optical microscope, still working in the near field, which is this time an aperture near field optical microscope, in which our sensor, our van der Waals heterostructure, is placed just on the bottom of the aperture, and in the near field and in the THz, so in this particular frequency range, can basically detect the evanescent component of the field which is behind the aperture. And this is quite nice because this can be used to make some kind of inspection on the micrometer scale of some biological tissues, cells, or resonators. And finally, just my last slides, we started also to work and we did some recent research on the development of inkjet printed components by using this van der Waals heterostructure, just creating some liquid film that can be used to demonstrate that we can devise novel optical components like mirror, reflectors, modulators, and saturable absorber that we recently demonstrated in my group by using this kind of liquid phase exfoliation of van der Waals material. And thank you for your attention.
Thank you very much. Maybe there are some questions. Yes, Eddie.
By these concentric rings that you make, like in a pond, is this this jet? Does it obey the laws of diffusion, or how? Fick's law? How does it work that you make concentric rings?
Yes, it works in this way. So you basically use a tip which has a dimension comparable to the wavelength of the optical beam that you are sending to the tip, and this tip acts like an antenna. So the tip can basically collect resonantly the frequency of the beam that is going through, and by putting the tip in very close proximity with the surface. When I mean close proximity, I mean something of the order of 10 nanometer. A nanometer is 10 to the minus 9 of a meter, so a very small distance. You can basically start to have a propagation of these waves starting from the tip over the surface. And this propagation is like a concentric propagation, exactly like when you put a stone in a water. And basically looking to these waves, you can unveil some particles, which are the surface plasmon, polariton, or the phonon modes, which generates over the surface of this material.
In general, you need like an activator and then a long-range inhibitor, no, to create these waves. Do you use such a principle?
Yes, the activator is the laser, and the laser is, of course, sending the beam through heat, and then the tip acts like the collector of these waves that start to propagate over the surface.
Yes, please.
May we see these waves as essentially planar waves, surface waves? Mm-hmm. No other direction, no other dimension. Yes.
So the kind of waves that you can have on the surface depends strongly from the material that you have. So there are some kind of materials that are also hyperbolic, and you can have some kind of hyperbolic waves which propagate on the surface. But basically with this kind of material that we studied, all of them are circular waves and planar waves, are basically surface plasmon modes linked over the surface of the material.
If you launch this plasmatic wave into your antenna structure, mm-hmm. It interacts with the material on the surface. You will get a back-reflected wave.
Yes.
And so there was an old paper published in 1989 by Ted Hench and myself, where we proposed that you then look at the interference between the back-reflected wave and a little bit of the incoming wave, mm-hmm. and look at the phase shift. Yeah. And so what are the prospects of using this as a very localized 1 nanometer microscope of the frequency response of the material on the surface?
So basically, all those things that we did is in the THz, so it's basically in the far infrared, so meaning that we are dealing with an exciting beam, which is basically a beam operating at frequency of the order of 100 micron. And the trick with this frequency range is that there are no commercial detectors that can work on this principle of detecting the backscattering like with the sensitivity that is needed with this kind of technique. So basically, another thing that we did in the group, we tried to use the quantum cascade laser, which is our pumped source, simultaneously like a source and a detector at the same time. So exactly looking to this principle of backscattering, the light is going back in the cavity, and there are some kind of nonlinear phenomenon that happens in the cavity that can be detected through a voltage change at the just 2 electrodes of the QCL. That is working like a detector. And we can just generate some interference fringes, like you said, and look into this kind of phenomenon in this way.
Just a follow-up question. Is it possible to consider, again, this very, very weak back-reflected wave, again, going back to old technology, mm-hmm. now in masers, of a maser amplifier, So to do what Charlie Towns did, to get a little bit of that to feed parametric amplification, is it possible to do something like that?
It's possible, yeah. We are working on that already, still with the QCL. Like I mentioned, with those kind of dynamics in the cavity, which is self-mixing, we can really look to those kind of phenomenon, even if it's quite weak in the THz, but we can.
I understand that you have recently invented some new kind of terahertz laser, the terahertz wire laser. Is it easy to understand what that is and how it works?
Yes, you mean which one? Because we did quite a lot, the combo or the random, or the wire lasers, because we did different kind of lasers. So which kind do we want? I can give you just a kind of overview of what we did about this invention of new lasers. Basically, the core idea is still using the quantum cascade lasers like a core device. And what we did, we make kind of study of photonic engineering solution to try to optimize some specific characteristics of the devices for making the quality factor of the laser itself quite high, which is a concept a bit difficult to achieve in the quantum cascade lasers that works with this respecting of the TM selection polarization rules. So what we did is that we recently devised a THz quantum cascade lasers frequency comb, which really work like a frequency comb over the full operating dynamic range of the laser, which is something that up to now has been not demonstrated so far, because there is the problem of the chromatic dispersion in the cavity that make not easier to really achieve phase locking between the optical modes. So we basically worked a lot on the suppression of the lateral modes of the QCL to have a full compensation of the chromatic dispersion of the laser. A second thing that we did, that I cited in the presentation, is that we demonstrated a random laser using the QCL, in which basically very differently from the standard Fabry-Perot cavity with whom a QCL is fabricated, this time we create a kind of random pattern on the surface of a bidimensional resonator, and we use it as a feedback to extract the light from the cavity, this random pattern. In this way, we completely suppress the distinction between the symmetric and antisymmetric optical modes of the cavity, just creating a light emitter that works with array additive quality factor optical modes. And those are two main things that we recently did with these QCLs.
Well, if there are no other questions, I'm pleased to give, in the name of our Academy, to the three awardees our very best wishes for your scientific future, and we are convinced that you will be satisfied to find new insights and help humanity in applications of scientific advance.
Yeah, thank you
I
very much.
like to thank the colleagues, for the academicians, for their fruitful contributions to the plenary session, which I am glad to terminate now.